So there's three types of transformations that we're going to learn about today. What does transform mean? It's a change, right? Like transformers, right? They change from one thing to another thing. So a transformation is when a shape changes in some way. Technically, it's a mapping of points from one location to another location. It results in a change in the orientation, in other words, how it's facing, size, or shape of the figure. A couple vocab words here. Pre-image is the image of the figure before it's transformed. So it's the original. And then the image is the resulting figure after a transformation. What does the word rigid mean? Yeah, Jake? So rigid means stiff or it's not like floppy, it's rigid. It's kind of the opposite of rigid, would be sort of floppy. So a rigid motion or a rigid transformation is a transformation that keeps the shape the same size and the same shape. The only thing it changes is the direction it's facing. So a rigid motion is, it only changes the orientation, not size or shape. So the way it's worded here is that it preserves the distance between the corresponding points, and the angle measures are preserved as well. In other words, the entire figure, if we're transforming a triangle, the entire triangle is going to be congruent in the pre-image and the image. It's going to be the same size and shape triangle. It might be pointing a different direction, but it's a rigid transformation, so it hasn't changed its size or shape. Yeah. There's a couple of new notation forms that you will be getting used to here. If this is our pre-image right here, and it becomes this triangle, I didn't trace it perfectly, but it's supposed to be congruent. Same exact size and shape. The pre-image is labeled with a J, K, Q. When you move that, each point gets moved in a certain way. J becomes J prime. You see that little dash? It looks like an apostrophe. We call that prime notation. So J becomes J prime. K becomes K prime. Q becomes Q prime. And that's how you can tell which one came first in this diagram. The pre-image does not have the primes, and the image is the result after you've moved the shape. and it has all the primes. So a couple of things here. This this right here, notation, it basically just says this triangle was transformed. That arrow is like it becomes this new triangle. Another way to read it is to say that triangle JKQ maps onto this new location. Okay, do the following transformations appear to be rigid? Why or why not? So, if this first one starts with the pre-image and this is the image, is it a rigid transformation? No. Why? It got bigger, right? So it's not rigid. What about this one? Rigid or no?
No.
Why?
Yes.
Yes, it's rigid. Yeah. Say if we folded this over right along this line, we folded it, they would match up with each other perfectly, so they're the same size and shape. All right, what about C?
Yes.
Yes. Same reason. Okay, so another word for a rigid transformation is an isometry. There are 3 types of isometries or rigid transformations. They are translations, rotations, and reflections. We're going to explore these one at a time here. A translation is a transformation in which every point of the figure moves in the same direction. They say it moves in a line. This is called the translation vector. It basically shows the direction that all the points are moving in the same direction, and they move the same distance. That's what keeps it rigid. Yep. This is like a slide. You're basically sliding a shape from one location to another location. You're not twisting it, turning it, flipping it, or anything else. You're just sliding it from here to here. It could be diagonal, left, right, up, down, but it's just a slide. So that's called a translation. I know it's confusing because the big word topic for all of this is transformation, right? That means it changes in any way, shape, or form. Transformation. This is a translation. It's literally just translate. You're just going from one thing to another location, just a slide. Okay, a reflection is a transformation in which it basically, it's like a fold, right? It reflects over a line of reflection. So there's always going to be like this folding line. You could think of this as like a flip. If something flips over. Did you ever in preschool take a piece of paper and you like paint on one side and then you fold it over and mush it together and you open it up and you're like, aha, now I've got the same painting on both sides. You ever do that? No? You should go home and do that. So that's a reflection, right? It's the same exact thing on both sides. Reflecting over this line. Now, notice here it says every point of the image is moved across the line. It's really moved the same distance. So notice here that like this is our pre-image point and it became, this point became this point. Notice that it's the same distance, right? From there to there as from there to there. Every point is moving the same distance across. From here to here is the same as here to there. So those 2 points are the same distance from that reflection line. So that's what this refers to here. The line of reflection is actually the perpendicular bisector of the segments that connect the pre-image and image points. So if you think of this as the segment that connects this point to that point, the line of reflection is actually going through it at a right angle and cutting that segment in half. The distance of each point to that line of reflection is the same on both sides. Okay, the last one is a rotation. You can think of this as a turn. Basically rotating around a point of rotation. We call it a center of rotation. So notice there's always a reference of where something is going to make these turns or slides or changes. This is a translation vector. It's showing the distance, I'm sorry, not the distance, the direction in which the translation is taking place. So which way do you want me to slide this figure? You need to have some sort of direction. A line of reflection, you need to know, okay, I have this figure, which way do you want me to reflect it? Over what line? And then a center of rotation. And this is where it's almost like an axle, you know, right through the middle. These are going to turn around this center of rotation. I always think of the hands on a watch, or the you know, like a ceiling fan or something, right? If you attached a triangle to a ceiling fan and turn the fan on, it's just going to rotate all the way around that circle, right? Always maintaining the same distance from that center. Just going to go around, right? Okay, a composition of transformations is just when you take a shape and you do more than one transformation to it. So 2 or more transformations done to the same shape. Like one after the other. We're going to practice that in a little bit. Okay, so this first one says reflect the figure across the line of reflection. So we start with this triangle. Here's our line of reflection. Remember, every point reflects on the other side of that line of reflection the same distance away. So this point here, you can kind of think to yourself, how far away is that point from the line of reflection, and then try to repeat that same distance on the other side so that you get an accurate reflection. It should look something like that. Number 2, translate. You're just sliding it, and again, they give you this arrow to show you what direction they want you to slide this in. Okay, so rotations get a little tricky. So we have a tool that we use to help us with rotations, and it's called patty paper, and I'm going to show you how to use it. Okay, so these exercises down here, they give you, in the first one, figure XYZ maps onto, remember that terminology, triangle ABC. Notice that the order in which they list these letters naming these triangles, is specific to what corresponds with what. In other words, if they write it XYZ maps onto ABC, you know X maps onto A, and Y maps onto B, and Z maps onto C. They do it in that specific order. So what is the image of angle X? So X is our pre-image. What does X become, in other words? Which point? A. So angle X becomes angle A. So that is the image of angle X. Name the side that corresponds to side AB. So in the first triangle, XYZ, which side corresponds to side AB? XY. And again, even if they did not give us this diagram, we could look at this statement they gave us and know that AB is the first two letters, and so it corresponds with the first two letters of the other one, XY. So if you look at this diagram, what kind of a transformation is it? A reflection, right? All right, you guys try example 3 here. Triangle LMN maps onto QRS by a, what is this one? Rotation, right? And you guys try A through D. Okay, so again, even if they didn't give you the diagram, you'd be able to answer these questions just by looking at the statement they gave you. LMN maps onto QRS. So what's the image of angle M? R. What's the angle that corresponds to angle S? Good. The image of LM? Good. And the side that corresponds to side LN? Good. All right, any questions on that? Now, moving things are hard to, it's hard to refer to locations of things when they're just randomly on a blank piece of paper. But if we put them on a grid, like a coordinate plane, then we can talk more specifically about the locations and where things start and where things end up. So it's useful to put these figures on a coordinate plane, then you can, move them in the more of a precise way. Did you ever play Battleship? It's like a perfect example of use of a grid, right? The locations would be very hard to describe if you didn't have some sort of numbering system for describing the locations. Okay, so we're gonna put our coordinates here of points A, B, C, and D. So point A is at the point -3, 3. Point B is at the point what? -1, 3. C is at -1, 1, and D is at -3, 1. So that's our original image. There's no primes. And it maps onto A prime, B prime, C prime, D prime. So let's put the coordinates of those. A prime is at 1, 1. B prime is at 3, 1. C prime is at 3, -1. And D prime is at 1, -1. Now they're telling us, and we could also see and count out, if we go from B to B prime, precisely how far or what direction do you take to get there? Well, you go to the right 4 and down 2. So the right 4 and down 2. And that will get you to your new location. So if you look at these coordinates, the x-coordinate of A is -3, and then the coordinate of A prime is 1. What do you do to -3 to get to 1? Add 4. So moving to the right 4 is just adding 4 to the x. So you can express that as this notation here. You start with xy, and it maps to, and this is kind of giving you like the rule for this particular transformation, add 4 to every x, and down 2, we're going to subtract 2 from every y. Let me write that over again. So that's one way of expressing it. This is another notation. See this right here? Those little carets like this, right? Instead of putting x plus 4 and y minus 2, they just do this little notation with a positive 4, comma, negative 2. It's still in the xy order. Positive 4 means you go to the right 4. Negative 2 means you go down 2. Okay, yep. So you're going to see both notations kind of on the worksheets and stuff. Usually on a test or quiz, I would include both so that you could, you know, kind of be clear about what we're doing. All right. This was a translation. This is a reflection. So this one specifically reflects over the x-axis. For the most part, when we do reflections, we're going to either be reflecting over the x-axis or the y-axis. You could reflect over other lines, but that gets a little bit more complicated. So in this example, we have point A here and A prime there. Remember that A is the same distance from your line of reflection as A prime is, right? And same with B. Should be the same distance to this line of reflection as B prime. So what happens to these coordinates? Point B, for example, is 1, 4. B prime is 1, negative 4. So if I were going to write a rule like we did up here with xy, xy maps to what? Well, look at the x-coordinates. -2 for point A and -2 for A prime. 1 for B and 1 for B prime. 3 for C and 3 for C prime. What happens to the x-coordinate? Does it change? No, it stays the same. So x maps to x. It's the same x-coordinate. Right, but what happens to the y-coordinate? 1 for point A becomes -1. 4 for point B becomes -4 for B prime. 2 becomes -2 for C prime. So how would we express what happens to the y? Changes in what way? Yeah, it becomes -1, multiplied by -1. So you're going to write it as like the opposite of y. Notice that if it was negative, if you do the opposite, it's going to become positive, right? That's still... now, this is a specific rule when it's reflected across the x-axis. That's not going to be true for every type of reflection, but always true for the reflecting over the x-axis. All right, now this example shows a rotation in the coordinate plane. It's a 90-degree rotation counterclockwise. We start with points A, B, and C. We rotate them this way, counterclockwise, to end up with A prime, B prime, C prime. The center of rotation is the origin, and we are always going to be using the origin as our center of rotation. It just makes things a little bit easier. Okay, so again, patty paper is helpful with rotations. This rotation, if we look at let's look at C specifically. If we start with xy, it maps to Well, this was 4, 5, and it became negative 5, 4. So what happens with the x and the y? They switch. So the y goes first, and the x goes second. Those two numbers switch order. But something else happens. The y value changed sign, right? The 5 became a negative 5, so it actually looks like this. And that's, again, only specific to 90 degrees counterclockwise. It's not going to be a rule for every single rotation ever. But in this specific case, that's the pattern that it follows. Okay, so this is an activity to sort of test your skills on the coordinate plane. And if you do it correctly, it's self-correcting, really. Let me explain how this goes. You're going to be following these steps, 1, 2, 3, 4, etc. Step 1 takes this first triangle A and gives you a transformation they want you to do to it. You can read what's in the parentheses. That's the clearest direction. Rotate. They want you to rotate triangle A 90 degrees counterclockwise about the origin. I definitely suggest you use patty paper here, but let me show you the best way to use patty paper on a coordinate plane. You want to make sure you trace the origin and your shape. Okay, so we rotated triangle A 90 degrees counterclockwise and got this triangle B. Reflecting, remember this point has to be the same distance on the other side of the x-axis because we're reflecting over the x-axis. Every point has to be the same distance. Then we're going from triangle C to triangle D by translating using the rule x minus 2, y minus 4. That's going to go to the left 2. So every point goes to the left 2, 1, 2, and down 4. 1, 2, 3, 4. That's your new point. Every point goes to the left 2 and down 4. Left 2 and down 4. So that is your new triangle, triangle D. Then move on to step 4, and you're going to reflect triangle D across the y-axis. All right, so you got to finish that last reflection and then make sure it maps to the smiley face triangle there. When we map this, this is 4 units to the left of my line of reflection, which is the y-axis, so I'm going to go 4 to the right. This one also goes 4 to the right. This one has to go 8. So that's triangle E. Now, we're going to check. If I go to the right 3 and up 7, will I end up on this smiley face? So to the right 3, 1, 2, 3, and up 7, 1, 2, 3, 4, 5, 6, 7. It worked. To the right 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, and then it maps, and then I know that I did it right. Okay. The practice that is attached to your packet, we're going to spend the rest of the period working on that, but it's also going to become your homework.